Hello students, in this lecture we are going to study heat transfer. So first we will start with the different modes of heat transfer. Then we will discuss conduction in more detail. After that we will see how heat will be transferred in case of conduction. That is, we will study mechanism of heat transfer in case of conduction. The next part will be the governing law of heat transfer by conduction, that is Fourier's law of heat transfer. Then we will discuss thermal conductivity in details, and we will see how thermal conductivity will behave with temperature. So first of all, we will understand what is heat transfer. So heat transfer is nothing but transfer of heat energy from high temperature region to low temperature region. Okay, so if two places are having different temperatures, then what will happen ki heat energy will transfer from high temperature region to low temperature region, and this heat energy is denoted by capital Q, and the heat transfer rate is denoted by capital Q, and unit for heat transfer rate is watts. Okay, sometimes we will denote this heat transfer rate by small q, and this small q is nothing but heat flux. Heat flux is rate of heat transfer per unit area, and this heat transfer rate per unit area is given by watts per meter square. Now we will understand the different modes of heat transfer. There are three modes of heat transfer. First mode of heat transfer is conduction, second mode of heat transfer is convection, and the third mode of heat transfer is radiation. So we will understand these three modes one by one. First we will start with conduction. Conduction is the process of transmission of heat from one particle of medium to another with particles being in direct contact with each other. Okay, so in case of conduction, what will happen ki two particles which are in direct contact, they will share energy with one another. So here we need to keep in mind one thing, that ki no particles are changing their location. So now we'll understand this conduction with some simple example. If you hold one metal rod in your hand and if you supply heat to another end of that rod, then what will happen ki heat will transfer from one end to another end, and this heat will transfer due to conduction. So in conduction, what is happening, the particles which are near to this left end of the rod, those will heated first, and those particles will transfer heat to the adjacent particle which are in direct contact, and this is how heat is conducted. So this conduction heat transfer is possible in all solid, liquid and gases, but it is dominant in case of solids and it is negligible in case of liquids and gases. Now we will understand convection heat transfer. Convection is the transfer of heat due to actual motion of molecules. Okay, so in case of conduction, we have seen that no molecules are changing their positions, but in case of convection, the molecules are changing their position to transfer heat. Okay, convection is the mode of energy transfer between solid surface and adjacent liquid or gas in motion. So in case of solids, we know that no particles are changing their position. So convection is not possible in case of solids, but it is possible at solid and liquid interface or solid and gas interface. So we can understand convection by some simple example like heating of water in a pan. So here we can see that we have taken water in a pan and we are supplying heat to this pan. So what will happen ki temperature of this pan will increase, and this heat will be provided to the lowermost layer of liquid, and now the liquid molecules will directly change their position and they will transmit the heat energy to the another layer of molecules. Now the third mode of heat transfer is radiation. Radiation is the transfer of heat due to electromagnetic waves in band 0.1 micron to 100 micron. So radiation heat transfer does not require any medium as in case of conduction and convection. In case of conduction, we have seen that energy is transferred between the molecules which are in direct contact. In case of liquid, the heat is transferred by actual motion of the molecules, but here we does not require any molecule. The heat is transferred without molecules, and that heat will be transferred due to the radiation waves. Okay, and most probably the wavelength band of those wave will be 0.1 micron to 100 micron. So example of this radiation is energy from sun comes to earth's surface due to radiation. So now we have understood all three modes of heat transfer, that is conduction, convection and radiation. Now we will discuss the mechanism of heat transfer in case of conduction. That means how heat is transferring in case of conduction. So first we will discuss how heat is transferred in case of solids, and then we will discuss how heat is transferred in case of liquid and gases. In case of solids, molecules are closely packed and cohesive force in molecule is very strong. That's why no collision of molecule is possible in case of solids. In case of metals, we know that metals are having free electrons, and free electrons take part in transfer of electricity as well as transfer of heat. So flow of free electron is the main mechanism in case of metals. In case of non-metals, no free electrons are available, and heat mainly transferred due to lattice vibration, as the molecules of solids are arranged in proper order, which is known as lattice structure, and vibrations in lattice structure propagates heat and helps heat transfer. Now we'll understand the mechanism of heat transfer in case of liquid and gases. In case of liquids and gases, heat is transferred due to molecular collision and molecular diffusion. Fourier law is foundation pillar in case of heat transfer due to conduction. So now we will understand Fourier law of heat conduction. So as per Fourier, the rate of heat flow through a simple homogeneous solid is directly proportional to the area measured normal to the direction of heat flow and the temperature gradient in direction of heat flow. Okay, so this is the statement of Fourier law. Now we'll understand this statement. So as per Fourier, rate of heat transfer, that is Q, is directly proportional to the area measured normal to the direction of heat flow. So this Q is directly proportional to A and temperature gradient dt by dx. Okay, so for example, if we are having any plane wall and we are trying to flow heat through this plane wall, then that heat is denoted by capital Q, and this Q is given in joules per second or watt, and we are flowing this heat through this surface area capital A, okay, which is normal to the direction of this heat flow, and this distance or this width of the wall is dx. So here we can say that we are supplying heat to this left face, so temperature of this left face will be more as compared to temperature of this right face. Okay, and here we can observe that there is some temperature difference in between this wall. Temperature at left end will be more and temperature at right end will be less. So that's why the change in temperature per unit change in distance is known as temperature gradient. Okay, so dt by dx is nothing but temperature gradient in this direction of heat flow, and this temperature difference per unit length is given by degree Celsius per meter or Kelvin per meter. So we have understood, according to Fourier law, Q is directly proportional to A into dt by dx. Now if I remove this proportionality sign, then I need to add one constant in this equation, and this constant is known as thermal conductivity, which is measured in watt per meter degree Celsius or watt per meter Kelvin. Okay. Along with this conductivity K, we need to add negative sign, and this negative sign refers that heat is flowing in negative direction. That means heat always flow from high temperature region to low temperature region. So now from this Fourier law, we will try to find equation for heat transfer rate Q. So for that purpose, we will again consider one plane wall of thickness dx, and we are passing heat Q through this plane wall. So at left end temperature is T1, at right end of this wall temperature is T2, at this end distance is x is equal to 0, and at the right end distance x is equal to L. Okay, so now what we will do, we will integrate this Fourier law with respect to these limits, temperature T1 to T2 and length 0 to L. So after integration, we can get Q is equal to Ka T1 minus T2 divided by L. So this is our equation to find rate of heat transfer through any wall. So if someone wants to calculate rate of heat transfer through some wall, in that case he should know thermal conductivity of that wall, then he should know the area which is normal to the direction of heat flow, and he should know temperature at both the ends of wall, and finally one should know length or thickness of this wall. So this equation also can be written by Q is equal to Ka delta T by L. So from this equation we can conclude that if you want more rate of heat transfer, in that case thermal conductivity of material should be more, because this Q is directly proportional to K. So now we will understand thermal conductivity in more details. Just now we have calculated formula for heat transfer rate Q, that was Ka delta T by L. Okay, so from this equation we will try to find equation for conductivity K. So K will be given by Q into L divided by A into T1 minus T2. Okay, so from this equation I can find unit for conductivity K. We know that unit for Q is watt, unit for length is meter, unit for area is meter square, and unit for temperature difference can be degree Celsius or Kelvin. So from that, unit for thermal conductivity K will be watt per meter Kelvin or watt per meter degree Celsius. So from this unit of thermal conductivity, we can define thermal conductivity by following definition. Thermal conductivity of material is the rate of heat transfer through the material per unit length per unit temperature difference. And this thermal conductivity is property of material. That means if you are having different objects made up of same material, so all those objects will be having same value of thermal conductivity. This thermal conductivity can vary with respect to temperature. So now we'll understand thermal conductivities of different materials. So in this table you can see that diamond is having highest value of thermal conductivity, that is 2300 watt per meter Kelvin. Then after diamond, silver is having second highest thermal conductivity, that is 429 watt per meter Kelvin. And you can see the sequence: after silver, copper is having more thermal conductivity, then gold, then aluminium, then iron. So in this table you can see that solids are having higher values of thermal conductivity as compared to liquids, and liquids are having higher values of thermal conductivity as compared to gases. So here it is important to note thermal conductivity of copper, which is 401 watt per meter Kelvin, then thermal conductivity of water, which is 0.613 watt per meter Kelvin, and thermal conductivity of air, which is 0.0026 watt per meter Kelvin. And all these values of thermal conductivity are at room temperatures, because just now I told you that values of thermal conductivity can vary with temperature. So now we will understand few facts regarding this thermal conductivity. Higher the value of thermal conductivity, faster the heat will dissipate through the material. So for example, if you are having two rods made up of different materials, for example, first rod is made up of copper and second rod is made up of iron, then in that case what will happen, here in this table we can see that conductivity of copper is 401 and conductivity of copper is 80.2. So heat will dissipate faster in case of copper. So you can feel that heat will dissipate faster in case of copper rod and heat will dissipate slower in case of iron rod. And reason for fast dissipation of heat is nothing but this Fourier law. Here we can see that conductivity is directly proportional to Q. So higher the value of conductivity, faster will be the heat dissipate through any material. Okay, materials having high value of thermal conductivity are known as good conductors of heat, and the materials which are having very low value of thermal conductivity, are known as insulators. Okay, so that's why diamond, silver, copper, gold, these materials are good conductor of heat, whereas wood, rubber, glass, fiber, these are the good insulators. Now we will understand variation of thermal conductivity with temperature. Thermal conductivity of metals decreases with temperature. When temperature increases, the vibration of metal ion increases, and this results in increase in resistance of metal, and hence conductivity of metal decreases. Thermal conductivity of non-metals increases with temperature. Thermal conductivity of non-metals are primarily attributed to lattice vibrations, and that's why the thermal conductivity of non-metals increases with temperature, and it does not show significant change at higher temperatures. Thermal conductivity of most of the liquids decreases with temperature. In case of liquids, except for water, aqueous solution and multi-hydroxy molecules, the thermal conductivity of most liquids decreases with temperature. The thermal conductivity of gases increases with temperature. In case of gases, as the temperature increases, the kinetic energy of molecules of gases also increases, and eventually collision between the molecules also increases, which increase in thermal conductivity of gases. So metals are having higher value of thermal conductivity than non-metals except diamond. Then non-metals are having higher value of thermal conductivity than liquids, and liquids are having more value of thermal conductivity than gases. So this was all about conduction, Fourier law and thermal conductivity. If you have any doubts, you can ask in comment section. Thank you.